Hi and welcome to Leetcode 118. Fun fact for you, there are 118 elements on the periodic table. Leetcode 118 is titled Pascal's triangle. It states, given an integer num rows, return the first num rows of Pascal's triangle. In Pascal's triangle, each number is the sum of the two numbers directly above it. I've drawn out the first 5 rows of Pascal's triangle for you. As you can see, we always add ones on the sides, and then anything below it is the sum of the first two above it. So 2 is the sum of 1 and 1, 3 is the sum of 1 and 2, 4 is the sum of 1 and 3, and 6 is the sum of 3 and 3. So the next row would be constructed such as 1, which can be thought of as 1 and 0. There are zeros here, but we just don't talk about them. And they go on for infinity, which is actually gives you the ability to go to negative rows of Pascal's triangle, but we won't be looking at that today. 1 and 4 make 5. 4 and 6 make 10. 6 and 4 again make 10. 4 and 1, 5. And with that hidden 0, we get a 1 here. This is an easy Leetcode problem, and there really is no trick to it. But it serves as a good exercise for how to take the ability of doing something by hand over to code. And with all problems, there are some things which are worth noticing here. The length of each row increases by 1 each time. So there's 1 element in this row. There are 2 here. There are 3 here, 4, 5, and 6. The leftmost element is always a 1. The rightmost element is always a 1. But how would we actually code this? I think one thing that's important when learning how to turn something like this into code is to first think about how you'll represent it in code. So let me clean this up a little bit. We'll rewrite it. So if we have 1, 1, 1, 1, 2, 1, and 1, 3, 3, and 1. The Leetcode problem shows it will return these as a list of lists. And so here, this would be one list. This is a list. This is another list. This is our last list. And we're returning a list of these lists. Let's call this list P for brevity, standing for Pascal's triangle. So P at 0 is equal to 1. P at 1 is equal to 1, 1, and so forth. The pattern kind of is a little bit hard to code for 0 and 1. So we can always just at the beginning of our function just put if num rows is equal to 0. You can just hard code return 1. And if num rows is equal to 1, just return 1, 1. And of course we could do this forever, but maybe that's not the best way to learn. So let's learn how to code from here with us having P, and now we have some indices. How would we actually code this? What's the rule here? So as we already have this, what do we now do for P2, right? Well, as we've seen, P2 0 will always equal 1. And P2 negative 1, meaning the last one, will also be 1. And more generally, P at any I, 0, will be 1. And P at any I, negative 1, will also be 1. But what about non-trivial, we could call this J, non-trivial elements? P at any I, well, we'll keep it at 2 for now, for some J. Let me make that a little cleaner here. Let's do P at 2, this third row, for 1. Well, that's equal to P at 1, right? These two, 0, and plus P at 1, 1. We know that this relation holds for all elements in Pascal's triangle, that P at some row R, let's call it, at some I is going to be equal to the row above it, R minus 1, plus the element to its left. And because we're padding it with the 1 on the side, this one is always going to be shifted 1 to the left, and then we're just going to be adding, let me go down a little bit, we're just going to be adding, ooh, that's gross, the row above us at the same index. So this is P1 0 and P1 1. More generally, this will always hold. This gets a little more complicated for the ones on the side because, as stated earlier, we're not representing those zeros. They really are there, but we're not supposed to return them, so we're not going to represent them in our array. Now, we have this general rule for any PRI, which is not on the edges, right? So for the beginning, the leftmost element in any row, we'll just set that to 1, and the rightmost one, we'll set that to 1. As we stated earlier, every row's amount increases by 1. Right? This one has 1 element, this is 2, this is 3 elements, this is 4 elements. As this is P2, it can be said, oops, oh no. Ooh. Ooh, I don't know what's happening. Let's ignore that. Okay. Let's just pretend that that never happened. Anyway, as I was saying, the len of any PI or PR, that's our notation, can be said to be R minus 1. And so if we were to start, well, let's clear our table here, and let's start writing some code. If we were to start with P equal to sort of our trivial rows here, 1 and 1, 1. And because we've got past those guard clauses of if num rows equals 1 and if num rows equals 2, we know that num rows has to be above 3, or above 2. And so we can loop through, and we can say for row r in range 2 to num rows meaning that we're starting at 2 because we've already set row 1 and 2, or rather 0 and 1, and so we're starting at 2. Let's make a variable for the new row that we're going to be constructing, and we can just set a 1 in there because we already know that it begins with 1, that's the leftmost element, and we're going to be doing the rest. Well, now how many elements are we going to be adding here? As we've said, the len of P at R is going to be equal to R minus 1. And we also know that, got right? R minus 1? R plus 1, right? We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This is R, this is P at 0, P at 1, P at 2, P at 3. My bad. It's R plus 1. And we know that 2 of them are always reserved for these 1s on the left and right. So the non-trivial elements are going to be R plus 1 minus 2. If that makes sense. I'm subtracting away these ones. And those are the ones that we're actually computing here. This will be 3. Right, so this is 2, 2 plus 1, so let's just do it formally. 2 plus 1 is 3, minus 2 is 1, and there's only one element here that we're actually calculating. As R goes up by 1 each time, this will then be 1 for this row, 2 for here, 3 for here. So this holds. Let's add our ones here. Anyway, that means that we will be looping for some I in range, how many? However many we're calculating. R plus 1 minus 2. Which is a little ugly. We can kind of just put R minus 1. Now that new row will be appending that sum that we calculated earlier, which is P at the row above us, which is R minus 1, at, now we said I minus 1, but because we're beginning at 0 here, we sort of already did an I minus 1, because we're always starting with the 1th element or the 2nd element, but we're beginning at 0 because I have already added this one. So we'll start at I, and we'll be adding P at the row above it with the next element, which would just be I plus 1. Once that's over, we've added all the non-trivial elements. Let's add back that trivial element, which is the one, the rightmost one. And then let's add this to P. I'm a little slanted here. And then finally, we can just return p. I hope that serves as an example of how to convert doing something by hand to how you'd represent it in code, to then getting a formula for what you're doing by hand in the new data structure you've made, and then understanding a little bit of how many times you're really going to loop with some little patterns that you've noticed. You can always, run your code 5 or 6 times where you just change that 1 to a -1 or a 2. But in an interview, it would be really great if you could explain why it's -1 and that it's really +1 -2, and that here you're looping through the non-trivial elements because you're already adding the one on the left and you're going to add the one on the right, and that you're following the pattern of how long every row in Pascal's triangle is. Yep, that's all.